And we got to the ideal gas law last time, PV equals nRT. What I'm going to do now is just show you real quickly how you can modify this to incorporate the density and molecular mass of the gas. So pressure times volume equals number of moles times the gas constant times the temperature. Another way of writing N is like that. Do you guys agree? The mass over the molar mass is the number of moles? Sure, why not? Right? So we can say PV equals. We rearrange this. See what I did? I just put the molar mass over on the left-hand side and the volume on the right-hand side.
How can you tell which is which?
What's that?
How can you tell which M is which?
Which M? This is my lowercase m. This is my capital M.
Oh. They all look the same. But it's hard.
In the book, you'll be able to tell more easily, and write my test because it's lowercase and capital. But mass over volume is what? What's mass over volume? Density. So we have so this is just another form of the ideal gas law. It's useful. In this form of the ideal gas law, there's no reference to any specific gas. It applies to any ideal gas. And you don't have to know what gas it is to use the ideal gas law. It applies to any gas that's an ideal gas. Over here, though, it does, right? Because the molar mass is going to depend upon what the gas is, right? So that's one thing that's useful. And it's useful because density, that's something that's pretty easy to measure, right? Take a known volume, measure the mass inside of it, that gives you the density. So you can measure the density, measure the temperature, that's pretty easy. Pressure, as long as you do it at atmospheric pressure, all you need is a barometer. So you can measure these variables real easily, and that will give you a handle on what the molar mass is, and consequently maybe the identity of the gas. What units, okay, following this little derivation right here, M is the mass in grams, this is grams per mole. What units do you think the density is going to have here?
Grams per mole?
Grams per liter, right? You guys are used to grams per milliliter, right? Okay, here's why it's grams per liter. This M, we said that it was going to be in grams so that it would work out with the grams per mole, right? To give us moles. So the mass is in grams. And the V, the volume, that's the same volume that we started with. And because of the units of the gas constant, the volume is always in liters, right? And so the V has to be in liters, and mass is in grams per liter. And I'm pointing that out specifically because that trips people up a lot. You're used to seeing densities in terms of grams per milliliter, grams per cubic centimeter, right? When you use it here, it has to be grams per liter, that's all. So the numbers are going to look kind of strange to you. First of all, gases have pretty low densities. The number of grams in a liter is going to be less than the grams in a milliliter, too. Okay, so these numbers are going to look small to you, but don't worry, that's how they work out. So I might as well do an example. All right, so when you see a problem like this, it involves a gas, and it's asking for, or it's giving things like density and molar mass. You're probably going to want to use this form of the ideal gas law. So let's see. It says calculate the molar mass. All we're going to do is rearrange that equation, solve for the molar mass. We just said we want the density to be grams per liter, right? So it's not, which means we're going to have to convert it. And you guys know how to convert meters cubed to liters? What's that? What's that, Travis?
1 meter cubed equals a liter.
No, 1 decimeter cubed is a liter, though. It's a really useful one to know. There are 1,000 liters in a cubic meter. You guys are frowning. Let me show you why. Okay, so that's true, right? And there's, so if we want to know how many liters is equal to 1 meter cubed, so if 1 decimeter is 0.1 meters, right? That's what deci means. 1 times 10 to the minus first meters. If we cube this, one decimeter cubed is 0.001 meters cubed, right? Right? You guys see what I'm doing? And so that means. So 1 liter is 1 times 10 to the minus 3 meters cubed, or 1,000 liters is equal to 1 meter cubed. It's just useful to know that one.
Do we have to do all that work, or is there a table for that?
You can just remember it if you want. There is a table, actually. This is, I think they give you this one in the back of your textbook.
Yeah.
And all that work, that was just to prove it to you guys, because they didn't look like they believed it.
Oh.
Anyway. This should give us grams per liter. So
It's 1.67.
times 1,000, divided by 1,000, it's the same, right? Let's see, what else? Temperature. You guys know that has to be in Kelvin, right? So we're going to add 273.15 to that. Pressure. It's in kilopascals. I think I'm going to use pascals. If I do use pascals, that's going to affect what value of R I use, right? So, and what is that table? I give you guys a table of gas constants to memorize. Remember that? In there, one of them tells you that one value of R is 8.31447 or something like that. Joules per Kelvin mole.
That's within
Yeah. And so what I want to show you is that that's equal to what I wanted to make sure you understood.
We're converting this to pascals, right? No, it's already in pascals. That's kilopascals. What? It's kilopascals. You just did 100 times 10 to the third pascals.
Basically, what I'm saying is that a
just say
joule is a pascal times meters cubed times meters cubed. Well, looking at it that way, right? See, I've got the meters cubed here. And my volume's going to have to be meters cubed, not liters. It's going to be grams per meters cubed. You guys see that? So I'm going to go back here and I'll do this. Are you whistling at me, Devin?
Single me out.
Everybody's looking at you. Anyway, you guys see what I'm doing here? No? What don't you see, Simon?
That's way too much math.
Ah,
Which one?
Is that 1.67?
They changed it back to.
Oh, okay.
so basically I'm doing
Oh, where did you
So I
get
could
the
cancel.
8.314?
4.7, 8.3145. It's
Standard?
Constant.
it's the one of the values of R in that table.
Okay.
It's on 434.
Page 434. Do you see it?
Yeah.
That is the value they give, right? They do 8.345 or 4.47.
Yeah, he did. Yeah, he didn't show the work.
So all I did is, hey Samsung, all I did was I took this form of the ideal gas law and plugged these into it. All this stuff over here is just making sure the units work out, which is the trick to all this. I'm making kind of a big deal about that because that's where people mess up.
Well, I thought that 1.67 times 10 to the third was part of that equation over there. Oh, okay. I just saw the arrow and I thought it was part of it.
So all this means that so I'm going from here, right? So what I did is this is the equation I'm going to use. I have used. These are the values of the variables, and I just got them in the correct units.
Oh, okay, so just.
Density, temperature, pressure, R. Then
You have the times 10 to the third
which one?
on the bottom?
Because the pressure that I gave was 100 kilopascals. 100 means times 10 to the third. I mean, I could have done 1 times 10 to the fifth, but all I do is I would take the prefix, replace it with what it means. That way I don't make any mistakes. Like I have the wrong decimal place. Anything else? Did you guys figure out what this number is? Yeah. That's what I'm telling you. A joule is a Pascal times a cubic meter. Yeah, about 40, right? See, 3 sig equations there.
0.04.
What are the units going to be? Hopefully grams per mole, right? Kelvin
What
cancels,
you got?
Pascals cancel,
I must have done
meters
something
cancel,
wrong.
we get grams.
No, you got it right on the
per
stencil.
mole. What's that? So again, I guess I can't emphasize enough, be real careful with your units, make sure they work out right. That's the way I get on multiple choice, where I get some of the wrong answers, is I do it all right, but I don't convert one of the units or something. If we rearrange the ideal gas law like we do in lab this week, solve it for R, dV over NT equals R. Now, if we have a gas that has a pressure or volume, there's a certain amount of it at some temperature. We take that exact same gas and we change one or more of these variables. Okay, so because we're changing them, it's the same gas. We're going to change them, we're going to label them. This is the subscript 1. It's going to be their values before they change. And then after they change, be subscript 2. It's the same equation, just different subscripts. So you understand what I'm showing? We have a gas, has some pressure, volume, number of moles, and temperature, and we're going to change maybe the pressure, the volume, maybe the amount, something, okay? It has a new set of variables over there. But it's still, but the PV over NT is still equal to R in both cases. Because you have, the left-hand side is equal to the same thing on the right-hand side. The left-hand sides are equal to each other. So we can say this. It's called the combined gas law. And this combined gas law is what you use if you have exactly the situation that I described. You have a gas, has some set of pressure, volume, number of moles, and temperature, and one or more of those changes. Then this is what you're going to use. And what you can do is, if you know that one or more of the variables is not changing, it's held constant, then that means, say it's n, it isn't changing. Then n1 is equal to n2, you can just cross it off. When you do it like that, you get all of the simple gas laws all in one. You get Boyle's law, Charles' law, Gay-Lussac's law, all of those, right? Remember Boyle's law? That was volume as a function of pressure. Do you remember the relationship between volume and pressure?
Inversely proportional.
Inversely proportional, right?
Yeah.
So that's what we can say. And what we did say when we were discussing Boyle's law is that we kept the amount and the temperature constant. N and T were constant. Because they're the same on both sides, they cancel out. You guys see that? And so what we have left is what's changing. This is a form of Boyle's law, or we could write it this way too. Charles' law. What was constant in Charles' law? What was Charles' relationship that he talked about? What was it between? Remember? Remember the gas thermometer?
Isn't it just a C? Like, you never actually told us what the C was, right?
Right, but what were the variables that we were dealing with?
V, volume, and
Temperature.
Temperature.
V and T, right? So volume and temperature were what we were dealing with. They were changing. And I said that pressure and the amount, pressure and N were held constant. So pressure and P and N cancel, then we get Charles. See how this works? And so, some of the gas law problems that you'll be solving are described by this situation. That is, you have a gas, some set of conditions, and one or more of those, the variables changes. If that's the situation, this is the equation you're going to start with. All you have to do is figure out what's constant, cancel it out. You'll have the equation that you're dealing with, solve for the unknown.
With Boyle's law, is it P1 over P2 equals V1 over V2, or is that right?
P1 over P2 equals V2 over V1, right?
Oh, okay.
You see? See how I got it?
Yeah, all right.
And you can see the inverse relationship. Remember we said when we started with Boyle's law, he said that the relationship between pressure and volume was an inverse relationship. It's not, there's that inverse relationship right here. Whereas with Charles' law, we said there was it was directly proportional, volume and temperature. There it is, volume, temperature, volume, temperature. One thing that just be aware of when you're solving these types of problems, if they don't tell you anything about the amount of gas changing, they don't somehow tell you that some gas is being added or some's being taken out, then you should assume that n's constant and cross it off. They won't always say anything about the amount of gas. If they say nothing, n's constant. Going on partial pressures. So you remember that balloon filled with helium we were talking about on Monday? The helium atom hit the inside of the balloon. Remember that, John? So going back to that picture, it was the balloon filled with helium, and those helium atoms are moving around inside of there, and they're exerting some pressure, and that pressure comes from each of them, from the sum of them hitting the inside of the balloon. And the pressure we see, if we look at the ideal gas law, is going to depend upon what the volume of that balloon is, how many of those particles there are in there, and what temperature they're at. Doesn't that make sense? So now let's take that same balloon and put some neon in there. It had helium, now we're going to put some neon. Before we do that, now let's take a separate balloon full of neon. Same volume as that first balloon. We're going to keep it at the same temperature, right? And put some neon in it. That neon is going to exert a pressure the same way, by hitting the inside of the balloon. And the pressure that neon exerts is going to depend upon how much neon there is, the temperature, and the volume. Okay, so far? We're going to keep the volume and the temperature the same. So however much neon we have, it's going to exert some pressure. However much helium we had, it's going to exert some pressure. Now we're going to take them, I'm going to take that balloon of helium, take all those neon rather, take the neon atoms, put them all in that balloon with the helium. And we'll close it up. So now the pressure inside of there is coming from the helium and from the neon. The helium is still going to exert the same pressure that it was before we added the neon, because it's at the same volume, there's the same amount, and it's at the same temperature. The neon, again, because they're the same volume, same temperature, and because we have the same amount of neon, it's going to exert the same pressure that it did by itself, because it's the same volume, same number of moles, and the same temperature. You guys buy that? So that means that the pressure on the side of the balloon now, when we mix those two gases, is going to be the pressure of the helium when it was in there by itself, plus the pressure of the neon when it was over there by itself. So what we can say in that new balloon is that the total pressure is equal to the pressure of the helium plus the pressure of the neon. Doesn't that make sense? In general, that's basically one statement of Dalton's law of partial pressures. But more generally, he says this. In a mixture of gases, the total pressure is equal to the sum of the partial pressures. That's what this is saying. The partial pressure, this, so the partial pressure, when we say partial pressure, we're talking about the pressure that one gas in a mixture would exert if it were under the same conditions by itself. In other words, the same temperature, same volume, same container, right? And there was the same amount of that gas as there was of that gas in the mixture. That kind of makes sense? Let's say I have two gases. Gas 1, gas 2. In this situation, where they're in the same container, so they're at the same volume and the same temperature. The partial pressure of the first gas is just, using the ideal gas law, nRT over V. Partial pressure of the second is nRT over V. The only thing that's different between these two is how many moles of the first gas you have, how many moles of the second.
That means the sum.
Times the sum.
The total pressure in there is going to be just the total number of moles RT over V.
It's not times the sum, it's the sum.
Oh, okay.
Yeah, so
Did you multiply them?
let's say
Okay, the symbol right next to the partial pressure.
for the sum.
Oh, this is sigma?
Yeah.
What I just raised?
Is that a variable for something, or is it just
No,
right there all the time?
this means the sum.
Oh, just trying to.
So we need to add them all up. For example,
No, I get it. It's the sum of the partial pressures.
yep.
All right, thank you.
Get it? You guys okay with that one? Have most of you guys seen that before?
Yeah, math classes.
Math class, yeah. Going back over here, we have just two gases. Total pressure is partial pressure 1 is partial pressure 2. Now I'm gonna define, I think you've seen it before, but just to make sure we're all thinking the same way, a mole fraction. The symbol for mole fraction is the Greek letter chi. Here's chi. In a mixture, the mole fraction of, it doesn't have to be a gas, but we're talking about gases. Of gas I would be the number of moles of I divided by the total number of moles. So. And the partial pressure of a gas is going to be the mole fraction times the total pressure in that mixture. Because if we take the ratio of the partial pressure of this gas to the total pressure, just write out what it means. You know, nRT over V, right? Because the RTs of RT over V's cancel. And so we have that's just the mole fraction. This is a useful expression for partial pressure of a gas. You see what it's saying? When we have a mixture of gases, if we know the mole fraction of that gas, that is how many moles of that gas we have and how many total moles we have, right? Mole fraction times the total pressure gives us the partial pressure of the gas. To do an example, because I think one of these shows up on your homework. Using mole fractions. guys, okay, as you're writing that down, the picture is this. You have two containers of gas, separate, right, they're individual. And in one of them, there's some helium. It's 400 milliliters, and the pressure of helium inside there, just helium, is 950 millimeters of mercury. The other one's 500 milliliters. It has just neon in it, and the pressure of neon in there is 700 milliliters of mercury. And then they're connected together, okay? And now the gas is mixed, so there's a new volume. The volume is going to be just the total volume of the two individual containers. And the gas is mixed, so now they're in a different volume. They're going to have each have a new partial pressure, and what we want to do is find out the partial pressures of each and the total pressures. Does that make sense? What do you think? Any ideas how to approach it?
Boyle's law.
Yeah, okay, pressure and volume, right? Yeah, you guys see that, Boyle's law? Because really what's changing for each of those gases is the pressure and the volume. For each of the gases individually, the amount's constant and the temperature's constant. So what we can say for helium, helium, it initially had a volume of 400 milliliters. What's its new volume?
900 milliliters.
900, because we're combining the two volumes, right? You guys see that? Do you see the picture? That's the picture that I'm trying to describe here. We have a 400 mil container, a 500 mil container, and then we connect them together. So they're open to each other. So the total volume now is going to be 900 mils. So V2 is 900. And the pressure of the helium when it was in 400 milliliters was 950 millimeters of mercury. This is going to let us calculate the pressure when it's in 900 milliliters. And that will be the partial pressure of helium. So, 422.2. Neon.
Why don't we convert that to liters or pascals? Yeah. You don't need it.
The initial volume was 500 mils.
Yeah, and it depends on ore. Yeah.
The final volume was also 900 mils because they're in the same container now. Its initial pressure was 700 millimeters of mercury. .9.
Yeah.
Notice we didn't have to convert the volumes to liters because they cancel, right? It doesn't matter if it's in liters, quarts, milliliters, what have you. It's going to cancel. So now we know the partial pressure of helium, partial pressure of neon. We answered these two questions, right? How do we get the total pressure?
Add 'em up.
Add them up. Dalton's law of partial pressures, right? Total pressure is the sum of the partial pressures. They do it. You should get that in your notes. I think you have a homework problem like that. Another example. So here we go. We have another mixture. And now I'm giving you the mole fractions of each. Helium and neon again. Mole fraction is 0.29 for helium, 0.71 for neon. And by the way, notice something about mole fraction, that the mole fractions always have to add up to be what? 1, right? I gave you mole fractions, I asked for the density. I gave you the temperature and the pressure. What equation do you think we're going to want to use? This one?
Charles?
Oh, no, okay, oh, this is different, okay? Notice the difference between this, nothing's changing. I'm just giving you some of the variables, right? But we're not like changing the pressure of the volume. Not like that previous example where we were changing the pressure, it was the same gases, still pressures and volumes were just changing, right? That's when you use some form of combined gas well like we do. Now, nothing's changing. We just want to find out what the density is. And I gave you some of the variables. What's it? Yeah, that's right. Okay, once the density of the gas, I'm probably going to use this. have a little problem. Not really a problem, I'll show you how it's not a problem. This is a molar mass, right? But we have a mixture, right? How are we gonna get the molar mass of the mixture? Because it's two gases, right?
Mole fraction.
What's that? And?
Find moles.
That's kind of the right track.
Mass percent.
Mass, almost, right? So you guys are thinking good, thinking well. But I didn't give you mass percents. What did I give you?
Mole fraction.
Yeah, why do you think I gave you that?
Grams.
Because we're gonna use it, right? Here's what we're gonna do. If we take the molar mass of helium times the mole fraction of helium plus the molar mass of neon times the mole fraction that's neon, that's going to give you the effective molar mass of the gas, of the mixture. Does that kind of make sense? Let me show you what I mean. Helium is 4.00, what? 2.6. Is it 2.7 up there? 2.6. 'See how the units work out?
Yeah.
This is grams of helium, moles of helium, times the mole fraction, which is really moles of helium per total moles. These cancel. This tells us how many grams of helium per moles total. We're going to do the same thing for neon and add them together. Watch. Neon's 20. That's the grams per mole for this mixture. That's the effective molar mass. Do you guys see that? Like that? So now we can plug that in here. We know the pressure, know the temperature. Good to go. What value of R do you think I'm going to use? Yeah. One with atmospheres in it, right? 19.2. The units work out like this: atmospheres cancels, moles cancel, Kelvin cancels. We're left with grams over liters. So that's it.
Why did you put 0.08 to the R?
Because the pressure was in atmospheres.
Oh, okay.
That's usually, that's what determines which value of R I'm going to pick, is whatever units the pressure in that gives me the R. All right, I should do this one too. Another time we're going to use Dalton's law of partial pressures is, as you are in the lab this week, we have something that's collected over water. Like if you did the lab today, then the hydrogen gas that was involved in the reaction, that was collected over water. And what that means is that the pressure inside of there comes from the hydrogen gas, as well as some of those water molecules. They're evaporating from the liquid, going into the gas phase, and they're mixing in. So it's a mixture of gases. And there's no way you can avoid that. Whenever you have a gas that's collected over water like that, then you're going to have some water molecules in with it. It's going to be a mixture. If you see words to this effect, this is the form of Dalton's law of partial pressures you're going to have to use. And so what it says is that the total pressure in that container is equal to the pressure of the gas that you care about, that you're doing the experiment on, plus this is called the vapor pressure of water. Like that table in your wagon. And the vapor pressure of water depends upon the temperature. The higher the temperature, the higher the vapor pressure. We'll talk about that more when we get to chapter 15. But the thing here that's important is you can look up. If you know the temperature, you can look up the vapor pressure of water at that temperature. So you look it up, you measure the total pressure like we do in lab this week. It's just because the system is open to the atmosphere, it's just atmospheric pressure, barometric pressure. So I read the pressure from the barometer, put it on the board, that's the total pressure. This is what you're going to need. So you just rearrange it. careful if an exam problem or homework problem says collected over water, or the experiment is set up so that it has to be collected over water, then make sure you do this on a multiple choice exam. One of the wrong answers would be what you get if you don't do this. You do everything else, but you don't subtract out the vapor pressure of water. So watch out for that. All right, so get this written down. So in this example, we have a mixture of salts. We have potassium chloride and we have potassium chlorate. When we heat them up, it ends up that potassium chlorate will decompose. It decomposes and it makes oxygen gas and potassium chloride. It's like this. So we have this mixture, we heat it up. Nothing happens to the potassium chloride that's in the mixture, but the potassium chloride, we assume it all decomposes, makes oxygen gas. We collect that oxygen gas. There's a picture of what the experiment might look like on page 447 of your textbook. You get 91.42 milliliters of oxygen gas at 22.34 Celsius instead of 68.32. What we want is the mass percent of potassium chloride. Okay. How would you approach trying to figure out how to solve this problem? What's the first thing you'd want to know? Or ultimately, what do you want to know, right, to get the answer? Maybe say that. What's that mass percent, right? What's mass percent mean? In this, this example right here, what is, specifically? How are we going to calculate at the end, the last thing we do? How are we gonna calculate it?
The grams of the compound over the total mass of the sample.
Exactly, right? So that's what we want, is we want the mass potassium chloride
Times 100.
over the total mass. But we know the total mass, because we weighed it before we did the experiment, 0.5199 grams. This is the last calculation we're gonna do to get the answer, right? We know everything in here except the mass of potassium chloride. So we need to get the mass of potassium chloride. How are we gonna get that? What do we know that can get us to that? What's that?
Molar mass? Oh,
Yeah, but we need the moles first, right? So, yeah, I agree. The molar mass will get us, if we can, so, okay, let's follow that, that's good. So, if we can get the moles of potassium chloride, we can use the molar mass to get the grams, right? But how are we gonna get the moles of potassium chloride?
With the moles of potassium
What's that?
chloride.
The equation, you just rearrange it,
Which equation?
the P divided.
Well, potassium chloride's a solid, and that's the ideal gas law, about gases.
And the amount of oxygen?
Yeah, there we go, right, Suzanne? That's why I gave you all this stuff about oxygen, right? And so now we can use the ideal gas law because it's a gas. So if we can use the ideal gas law to figure out how many moles of oxygen, N for oxygen, now we can use the balanced equation to get the moles of potassium chloride. And we can use the molar mass to get that. You see how that works? See how you figure that out? Right?
We try.
So we're gonna,
Just use ideal gas law for this one. To find moles.
this is what you guys told me, okay? We want to get the moles of potassium chloride so that we can get the mass, right? Use the molar mass. And then you told me that to get that, we need the moles of oxygen. And then we can use the balanced equation to get the potassium chloride. And then, you said, to get the moles of oxygen, use the ideal gas law. So now, okay, so to get over here, we see where we have to start, right? What we need is the pressure of oxygen, the volume of oxygen, and the temperature of the oxygen. Did I give them all to you there?
Yes.
Yeah, pretty much. Okay, so let's do it.
So we keep the pressure until what do we do to 18?
What's the pressure?
Pascal.
so
No, you can use Tor. Yeah,
Hopefully.
you just have to.
That would be the wrong answer.
Oh.
7
Yeah, use Dalton's law of partial pressures, right? That's why I'm doing this problem here, kind of.
747.82.
That's what, that number right there. That's the total, you see that picture? That's the total pressure in there because that's going to be the atmospheric pressure. That's going to be what I read off the barometer. Okay? But we need the pressure of just the oxygen by itself. The only way we can get that is to calculate it using Dalton's law of partial pressures. That is, subtract out the vapor pressure of water at that temperature. You guys see what I'm saying? Everything else is pretty straightforward. Volume, I gave it to you in milliliters, and you know you need liters, right?
When you do these problems, you just write down all the variables and just match it with the equation, right? What equation you're going to use? Yeah, with this, with basically, to find all of that.
So what do you want to use for R?
62.3637.
62.
What?
2.3637. Weird, and four rooms.
Like that, right? Yeah? You guys get that number?
Sort
The
of.
volume, is it 0.0941 or 14?
Oh, did I do that? Oh, no. What did I say? I erased it too, right? Did anybody write it
It's
down?
on-
It's right down the right.
.9142.
It is 9142?
Yeah.
So this is different. Thank you. All right, anybody get the right number?
371. Then it was like 01.
Like 01 or 01?
01.
So, okay, so you see, so now, we use the ideal gas law, making sure we did the collected over water, the Dalton's law, partial pressures and all that. We got the moles of oxygen. Now I can use the balanced equation to get the moles of potassium chlorate. Use the molar mass to get the grams of potassium chlorate. And we're done. Oh, then count. Molar to mole ratio from the balanced equation is 2 potassium chlorates per every 3 oxygens. Now grams using the molar mass. Now that we know the grams of potassium chlorate, we can just plug into here. We have our answer. Stop here. I still have some left to do in chapter 13. I'll do that on Monday. This is kinetic molecular theory, Graham's law of diffusion, free path, torsional frequency. Sorry?
Yeah, it's written all the variables, it just matches up with the equations, but
That was
did you get it?
here.
Almost. Oh, that's